Two. Okay. How's everybody doing?
It's great.
Anna is here,
Yeah,
just not
went out.
right here. Okay. So today we're going to talk about the reading that I forgot to move when I moved the other thing, but everybody did it anyway, so cool. And then we'll get into that stuff. So I had threatened to talk about Green's functions, and then I decided I'm not actually using Green's functions anywhere. It's just cool that when you have, if your equation looks like d by dt of q, the tiniest headed q ever, equals d del squared q for whatever q is. Q might be density, it might be a fart in a room, it could be all kinds of stuff. This is the diffusion process, and we talked about this, where it comes from. So it comes from random walk-like processes. So this is useful when we're talking about the molecular diffusion level. So when we're at a very small scale, the very, very, very smallest scale, where atoms are smashing into each other, and the velocity of an atom is the random sum of a bunch of collisions with other atoms. When you have that random sum, then you get a Gaussian in the process. So this gives us Gaussians, and also we can say that if I have my mean squared displacement of a particle in that in a system that is exhibiting this kind of turbulent diffusion, or not turbulent diffusion, molecular diffusion, x squared goes like d times t. Or the RMS velocity goes like the square root of, or the RMS position, x RMS, goes like the square root of t. So if you're talking about how far away from the origin you expect to be after a time t, it goes like the square root of t if it's a diffusive process. This is at the molecular level. So now what I'm going to do is talk about walking up through various size scales until we get to larger than the turbulent size scale. So let's talk about the ocean. The ocean is a big place. And we can really easily assume that we're larger than the turbulent correlation scale as long as we're pretty big. So what I'm going to do today, and I'm actually not going to get into it, I'm going to talk about the reading questions first because they seed a lot of these thoughts. So what I'm going to do is start at the molecular level, and then look at the small scale, and then large scale, and then medium scale. And I'll explain what I mean by this. I mean something specific between all these things. So I'm going to basically talking about if I have two particles and I put them in the ocean really close together, they'll walk away from each other by molecular diffusion initially, but then they'll get picked up by the turbulent cascade, and then they'll move away from each other much faster. So we're going to talk about all these. Let's go through the reading questions first real quick, because they're interesting. Why is the outer layer of stars turbulent but the core is not? So that's really a question for Intro to Astro if you want to take Intro to Astro, or find somebody who has a digital copy of the Big Orange book. But I'll show you the basic idea. So if you remember this buoyancy business that we did, we got a criterion that says that basically ds dz has got to be slower than adiabatic. So as my plume rises, if it gains a lot of entropy, then it's going to keep rising. But if it doesn't gain any entropy, it'll sink back down again. Do you remember doing that? So I talked about it, but I didn't make you guys put your hands on it very hard. So things don't stick as well. But basically, this is the Schwarzschild criterion that we derived in class a couple weeks ago, that if the background star or the background pot of water or whatever, if the process is fast enough that the density when you raise a little blob up is lower density than the surrounding material, then it'll keep going up. So we have a similar situation in stars. So in a star, you can turn this into a criterion on when different parts of the star will be convective or not. So the small, in the interior part of the star, for small stars, the interior part of the star does not have the right entropy gradient to be convective, so that material basically stays there. It's stably stratified. So in the low energy, in the interior region, it's stably stratified. But then as you get to the outer regions, then you get to see this 3.6, 2.7 Kelvin. So then you get to, but then when you get to the upper level, then what you see is this very large temperature gradient, because outer space is very cold or very hot, but there's low density. There's very low density out here, so the energy can escape. So you get a very large temperature gradient, and that temperature gradient drives convection. Does that make sense? So big temperature gradients drive convection is the real takeaway. When you have a large temperature gradient across a star, then you'll get convection. So depending on how close you are to the surface and what's going on, and what the overall temperature gradient is, you will have convection some of the time and stable strata some of the time. And when you get into the details of stars, if you talk about really little stars, they're fully convective. But then as you get to bigger and bigger stars, they start to stratify because the temperature gradients aren't that big because the star is so large. Because and whenever you get this convection, it becomes turbulent basically immediately. Because whenever the flow is complicated, whenever the Reynolds number is large, and this is a star, so L is huge. Whenever the Reynolds number is large, you're going to get turbulence, and there's really no way around that. What is the biggest scale that we can see? So this is a super interesting question. And I think it's, yeah.
I just want to ask you real quick. So turbulence is like, when a system is turbulent, that means that their motion becomes unpredictable, or?
Yes.
So is that, how is that like not chaos or something?
It is.
It is? Okay.
It is also chaos.
Okay, okay.
So the turbulent flow is also chaotic.
Okay.
Now, you can have, okay, chaos is an interesting question because a fluid is chaotic, but it is not the only way to be chaotic. And this is something, one of my very favorite lectures that I did in this class was like this first time I went through it. Ruby Kay was a fluid dynamicist, and she retired. But she was about this big, and she was like 100,000 years old, and she knew everything. She was the most delightful. She was such a sweet little old woman. I miss having her around. She was great. So anyway, she came in and did some demos for this class. I have, in various instances of this class, have really cool demos, but I don't have anybody to run them now. Sorry. And so I'm gonna take an aside and talk about chaos because I don't have a huge agenda today. So what is chaos?
You after me?
Yeah. Or somebody else, anybody else can jump up. What does chaos mean to you? And there's not one.
Is it like an unpredictable?
It's unpredictable.
You can't like write down equations.
You can't write down an equation to describe it.
It's almost pseudo-random.
Pseudo-random or potentially completely random. I would argue probably completely random, but hard to say. One of the real important things is sensitivity to initial conditions. Have you heard that phrase before?
Yeah.
This is the butterfly flaps its wings in Asia and you get rain in Sumatra.
Right, you get that from the pendulums too, right? When
Exactly,
depending
exactly.
on the starting condition.
If you take two double pendulums and you start them at what you think is exactly the same position and let them go, they're going to do things differently because you didn't actually get the initial conditions right. You didn't actually match it. And so that's chaos. Now, you can have a chaotic double pendulum, and that isn't turbulent, but it is chaotic. In fluids, you can have, most of the time, chaos comes with high Reynolds number. But you can also have chaotic flow in low Reynolds number because fluids are persnickety that way. But I don't know, I'm just going to describe, if I could do it, it would be really cool, but I'm going to describe the experiment that she did. So she took a dish, a Petri dish, and this Petri dish has two upended test tubes in it. So there's these, so your boundary condition is the outer wall, and then these two things that can spin freely. I'm going somewhere interesting with this, I promise. Now, if I take, and it's filled, oh shit, I haven't shown you guys the reversibility movie yet. I gotta do that. Sorry.
You have to write that down.
I do have to write that down. I have this list of things that I'm going to put into a bunch of slides that are like graphics and visuals that I'm going to bring up on Thursday. NSF films. Because really, there's this one thing in one of these movies that just, every time I watch it, it blows my mind. Every time I see it, I'm like, it can't be real, but it is. Yeah.
Is there a reversibility one where you have like a crank and like a certain kind of viscous liquid, you put like a piece of dye in it,
Yeah.
you drop the dye, you turn it, it's all strangled, then you unturn it and it goes back.
And it unmixes. Yeah, it unties. So, okay. Let's see if I can find it real quick. So they released these movies in, okay. Oh, let me talk about that. Going off on tangents with me. Oh, I gotta turn this blinker on. So, okay, I'm gonna come back to chaos. I'm gonna come back to chaos in a second. And then I'm gonna talk about fluid chaos. But
Yeah, it's not very. Oh, really? But they're like an hour.
no, stop. How do I make you stop?
That was cool.
Okay, so oh, I gotta plug it in. That's why it doesn't work. Okay.
How old is that?
1955 or 1965. And this is G.I. Taylor, who is he's the Jesus of fluid dynamics. He's a super important.
Reynolds number flows are those in which inertia plays only a very small part in the conditions which determine the motion. Reynolds number for a flow which is characterized only by density and viscosity is defined as R equals L V rho over mu.
This is new.
Here L is a
V over
length
rho is mu.
characteristic of the field of flow, V is a characteristic velocity, rho and mu are the density and viscosity of the fluid.
Okay.
The momentum of flow is reversed.
Okay, remember when we did a problem on what I call plane parallel Couette flow, where you had two planes and they're moving with some velocity, and viscosity sets up a velocity gradient between the two of them. Okay, you did that for a homework problem. Now, I did it plane parallel just because cylindrical geometry is a headache, but and doesn't get at the physics that I want. But if you can do it in a lab much easier if you just have a cylindrical tank and then a smaller cylindrical tank on the inside, right? So then I can rotate the inner one and make shear happen in the outer one.
This may lead to some surprising situations which might almost make one believe that the fluid has a memory of its own. Here
Water
are
doesn't
two
have any memory,
concentric
despite what the
cylinders.
homeopathic people tell you.
The
That's like that.
fluid can be moved by turning the inner cylinder with this handle. The annulus between them is filled with glycerine.
So glycerine's real
Into
thick.
this space, I introduce some dye, which stays put owing to the high viscosity of the glycerine. Note its position before I start turning it. I now turn it 4 times. reverse the direction.
Which my gut says is just gonna make the problem worse. It's like doing dizzy spells when you were a kid and then trying to
But after
undo it by
turning
spinning
it
the other
back
way.
before it turns, the dyed
That
area
doesn't work.
reappears in its original position, with a little fuzziness due to molecular diffusion.
No, I don't like that.
There. And there it is. Oh no, it gets worse. There's a worse one.
To see what happens, we have a second apparatus that is filled with syrup. It has a wider gap, and we can look down on it. A little colored syrup is injected to mark the fluid.
Here he makes it square.
Oh, God.
When the cylinder is turned, this fluid is stretched around the annulus.
Watch how close these things get to each other. That's important. You can't tell because the video is terrible. But these two lines get very, very close to each other. And that's important for what I'm going to talk about in a
Now the
second.
inner cylinder is turned back exactly to its starting position.
I know, right?
The boundary
But this is the issue.
path determined at each instant by the motion of the wall.
I wouldn't realize what was happening.
At these very low Reynolds numbers, particles within the fluid move when the boundary moves, and they stop when it stops. During the reversed motion, the boundary of the fluid position. The motion of a rigid body is also reversible.
It's
Here's
like
where
goddamn
the
magic.
markings orient.
All right, so if you do this same experiment, but
Wait.
what's that? Oh, yeah, maybe we should talk about that part.
Yeah, no, yeah. So, that's kind of like when you put a Sharpie on like an elastic band and
Yeah.
then stretch the elastic band.
Yeah, a little bit, yeah. It's not entirely different because in this flow, because the Reynolds number is so low, the velocity is never very high, so you don't get any mixing. You don't get any, the particles basically all stay on annuli, so they're kind of constrained to just move on the ring that they're born on, because that's all the motion that happens is in that ring direction.
It's kind of like a puzzle piece where you got rings that move at different speeds.
Yeah.
But if I took that thing and I attached like a drill to the top of it,
Oh, yeah.
it would create turbulence and it would not go back.
Right. You can make chaos without making a drill. So if I take two of these, and this is the thing that Ruby K showed me. So you take two of these setups and you put them next to each other. And I put a stripe of water, or a stripe of dye like this, and then I spin this one, it gets wound up. And then, if I spin this one, these two lines also get wound up. And because the lines get arbitrarily close together, do you remember how close together it looked like those lines were getting? That's accurate. If you keep going and you spin it a couple of times, you'll get lines that get very close together. You get these lines, so even if you just put in one stripe, you spin this a couple times and you get like a spiral. And then if I take this one and I spin it a couple of times, then I get another spiral that has these tiny little filaments. And if you pick a filament and you follow it backwards, one filament takes you over here, and another one right here takes you to the other side of the box. Because when you do this double mixing, or when you do this double Couette flow, then you get very, very sensitive to the initial conditions, because that's what fluid mechanics wants to do. So this is a chaotic flow, even though it's like that one, it's a very, very low Reynolds number. It's very slow. So you can have chaos without having turbulence in something like this, but you can't have turbulence without chaos. So anyway, that's a very cool thing. So that's very, very low Reynolds number flow. And we're talking about the opposite extreme, which is very high Reynolds number flow. If you take a drill, or if you just are careless when you do that, like you don't have to spin it very fast to make things become turbulent. Yeah.
I'm just confused how the blob or the square retains its shape. Like even if it comes back, how does it retain its exact shape?
Because every particle goes right back to where it started. So you're going to get a square again. Thanks, I hate that. So you start off with a square. It gets, like, each particle remembers its R theta location.
How?
Because the flow is so slow. Because it doesn't have to. Kind of like Anna's description. If you have a rubber band and you write on it with a Sharpie, you stretch it out. You can stretch it in a whole bunch of ways and make it look really distorted. But then when you relax it, everything goes back to the same spot. Does that make sense? So that's true because you have polymers that are tying all the spots together. This is true just because the flow is really slow, so you never cross. So you have these. Let's call these are lines of constant radius. So this is one radius, and each particle remembers its theta position and R position. So if you distort it and then undistort it, they'll go back to the same spot. Because at no point are you going fast enough to cross one of these lines. As soon as you cross one of those lines, then it starts to mix. As soon as the Reynolds number gets large, then it starts to mix. As soon as you get any this direction motion, which if everything's really slow, you should never have any radial motion. But that's what turbulence does. As soon as the Reynolds number starts to get high, then you start to get some radial motion, and then it goes away. But without any radial motion, without any radial mixing, all we have is annular mixing, or all we have is annular motion. Then you can just put them all right back because they'll just go right back to the same spot. It's pretty.
Even if the particles kind of mixed together with each other, they still that same particles at the top right corner would still be there when you make it go back.
Yeah, it doesn't. You can't push this all that far. If you go around 11 times, then you'll be in a situation like this where the lines are so close to each other that you can't tell which one started where, and then any molecular diffusion, and there is some, will wash it out. So if you go around 11 times, then you'll come back. It'll be in kind of the same spot, but it's not going to look like a square anymore.
Which is what happened with the dye case, because he went 4 times, and when he came back, there was some molecular diffusion and it kind of looked like a blob. But
yeah, it gets a little fuzzier,
yeah,
but not so much fuzzier. So, okay, yeah.
So for the one too, where it turns into chaotic motion, since you know the initial conditions, can you predict the motion of a particle, or is it
No, it quickly becomes unpredictable. It's so.
Even if you know the initial?
Yeah, even if I knew exactly what I did in both of these, once it gets chaotic, then it doesn't matter how well I think I know what I did. I never know it well enough. There's always, whatever you do, there's an error associated with it. Every time you make any kind of measurement, there's always an error. And that error, no matter how small, is going to kill you if it's truly chaotic. Now, if you take that logic down to its ultimate limit, then you run into Heisenberg's uncertainty principle, which says that even if you know everything perfectly, you still don't know everything perfectly. So Heisenberg will always stick his finger in and make things chaotic when you don't want them to be. Any other questions about chaos? Yeah.
So if you just took that blob in that fluid and just let it sit and molecularly diffuse for a while, versus if you spun it up 11 times or something, and then let it diffuse for the same amount of time, and then unspun it, would your apparent diffusion of the original blob be much bigger because
no, those two operators don't commute.
Ooh.
So you would be able to tell if you knew what you were doing. You would be able to tell which one you did.
Okay.
Because when you mix it, it's going to get a lot fuzzier.
Okay.
Because then you've got these tiny little strands, and they can mix, but that tiny little strand needs to go back to something that's larger. Because you start with a blob like this, and you stretch it out, and it gets tiny and tiny and tiny and tiny and tiny and tiny. The thinner that line gets, the worse of a chance you have at getting back to the original spot. Okay. So once that line gets thick like the molecular diffusion layer, then everything is just going to get washed out.
Okay.
Yeah. Okay. Where even was I? Oh, I was in.
So you finished the stars question.
Yeah, I'm on the second question, and that's all right. Anyway, this is the stuff that keeps me going, so I like this stuff a lot. I think it's very fun. Okay, what's the biggest scale that we can see? So that's an interesting question. And while I have this thing up, let me show you a very important measurement. Well, Dropbox, talks. So, okay, now I gotta guess which one of these did I? Excuse me. Where did you open it? Did you open it over there? No.
It's like a close and quit.
Yeah. Not in that one. I'll pull up. I have a list of movies that I'll show you in that. Boop. I have a bunch of movies that I'm going to bring up on Thursday. I'm not going to try to look for them right now because I'm not going to find them. Okay. So the largest scale. So this is an interesting question. What's the largest scale that we can see? And the question means a couple of things. The first answer is just what is the actual biggest thing that we can see? And probably the biggest thing we can see is the cosmic microwave background, or fluctuations in the cosmic microwave background. But the biggest thing that we can see that's turbulent is probably the gas in big clusters of galaxies. Big clusters of galaxies are the biggest gravitationally bound objects. Probably there's arguments there are some other superclusters that are like 200 gigaparsecs across that are gravitationally bound, but that's not clear that they're actually that. The big balls of dark matter that are galaxy clusters are really the biggest objects we could see, and they are filled with this X-ray emitting gas. And if you can measure, and it's tricky to do it's tricky to actually measure in one of these galaxy clusters, but if you can measure the velocity power spectrum, so the power spectrum is this E of k versus k. So this is called the power spectrum. And if you start to see this nice power law where E of k goes like k to the minus 5/3, then you know that the solution is turbulent. So there's some argument, there's a lot of arguments that galaxy clusters are the biggest turbulent objects that we can find. That's truly a single ball of turbulence. And it doesn't have anything to do with the galaxies, it's the gas that they live in. The gas that they live in is this 10 million degree X-ray gas. Yeah, but that's an interesting question. So one of the things that we can tell from the CMB, so when we look at the CMB, we can see a spot. So if the CMB is this big, we can see spots that are like this big, and we know that this is the size of the causal horizon. So this is the size, this is the distance that light can travel from the beginning of the universe. And we can see several hundred copies of that all over the sky. And they all look the same. So we know that our universe has several hundred copies of this universe around us. So even though the causal horizon is 15 gigaparsecs, or 15 billion light years, we can tell that the universe is bigger and more homogeneous on a scale several hundred times larger than what we can actually observe, because we can see the imprint of those other universes on the cosmic microwave background. That's kind of off topic. Okay, these derivations are getting hard to look at. It's not wrong. Galaxies have magnetic fields, yes. I will show you, the galactic magnetic field has gotten so much more interesting than when the book was written. Because now we have good maps. So Planck released a good map. That's one of the things that I'll show you on Thursday, is what the galaxy magnetic field looks like. That's something that I spend a lot of time on, is galactic magnetic fields. I spent all day yesterday trying to make a simulation go to measure galactic magnetic fields.
So at those scales, are they like massive magnetic fields?
No, they're tiny.
Uh,
Yeah. So how big is a magnetic? We'll talk about magnetic fields more in like 2 weeks. Sorry. I forgot to talk about administrative business. Homework. It'll be a homework, and I promise I will get it up tonight. So before the end of the day, and it will be due, and it has to be due next Tuesday, because as per my schedule that's been online, that hopefully everybody's been looking at, the midterm is next Thursday. So we got a midterm coming up, so we'll do, today we're gonna talk about diffusion. Thursday we'll talk about complicated stuff, and then following Tuesday we'll review everything, and then Thursday will be the midterm, if that works for everybody, yeah.
Can we have our homeworks graded?
Yes, that was the other thing. I promise I will have all of your homeworks graded by the end of the week. If either the homework doesn't go up today, or the homeworks aren't graded by the end of the week, I will move the midterm, because you should see how I grade, because I kind of suck at getting the grading. But I'm a pretty easy grader, but you should get a flavor for what kind of a grader I am before I throw you at the midterm. But the midterm's not going to be all that much more complicated than the homeworks. If you could do the homeworks, then we'll do the midterm. So I promise I'll get to those things. Okay. How does the atmosphere treat the boundary with space? And this is an interesting question, because it doesn't make sense as a question, because there isn't a boundary between the atmosphere and outer space. There is not a point where you can say this is where outer space starts. There are things like the Armstrong line. The Armstrong line is the altitude where the vapor pressure is low enough that water boils at room temperature. That's the Armstrong line. So you can't exist above that line even remotely, because all of the blood in your body will boil, and that's not fun. So that is one definition that people can describe as the beginning of outer space, but there's still plenty of gas that goes way, way, way up. So it deals with the pressure, it deals with the edge by not really having an edge. The density just goes down basically exponentially, and then mixes with something else. So there's the Van Allen belt, so we have these big magnetic fields that wrap around the Earth, and those start changing how the galaxy forms. So there's not really a well-defined boundary to that atmosphere. So that's an interesting question, and the answer is interesting too. Can you explain the Reynolds stress? That's what I'm going to do today. Can we ever describe turbulence without a statistical theory? No, unfortunately, because it is fully chaotic and it is fully unpredictable. So you have to talk about it with some averages. I realize I'm not in a shot for any of this, so it doesn't make sense. I'm just off camera talking. If I move that, then maybe I won't be off the camera. Okay, mixing length theory. He touches on mixing length theory and then doesn't go into it. I will show you what mixing length theory is on Thursday. Where does turbulent diffusion theory fail? All over the place. Wherever all of the assumptions that you made going into the turbulent derivation are broken, and there are many, and they get broken very easily. So homogeneous and isotropic is easy enough to break if you have a boundary that's anywhere near your flow. Yeah.
In like space, astronomical phenomena, when like there's turbulence within material, and that causes like the magnetic fields to change. Can magnetic fields also like have their own turbulence because of that?
I wouldn't say that the magnetic field has its own turbulence. I would say the whole system has turbulence. But the magnetic fields will follow the flow and get tangled. And then you can amplify magnetic fields that way. So we'll talk about dynamo theory. I'm pretty sure we're going to get to dynamo theory because we're going actually kind of quick. So I have a couple lectures on dynamo theory at the end that if everything goes smoothly and there's not another hurricane, then I think we'll actually get there. So dynamo theory is taking a magnetic field and stretching it and making it stronger just by motion of the fluid and the magnetic field itself. And when you have a turbulent flow, then you have lots of little scale motions in both the magnetic field and the fluid velocity, and they interact. And their behavior is different at different scales, so it gets kind of hairy. But hopefully, I think we're going to get to it. So in principle, we're going to do MHD turbulence as well. Knock on wood, if we get there. What is anisotropic turbulence like? So the simplest anisotropic turbulence that one can come up with is in a rotating system. So if you have a tank of fluid and you start it rotating and you just stick a grid in it, then it will make turbulence and it will make eddies that all line up. So you'll get these like tornadoes that all line up along the rotation axis. It's very fun to watch. But it's still turbulent. It just behaves slightly different. So when you have a rotating system, you don't get this k to the minus 5/3 anymore. You get something else. And you can predict that to an extent. Let's see. Is the equipartition of energy in the galaxy? So the equipartition of energy in the galaxy is very interesting. So the total magnetic energy, the total turbulent energy, the energy in supernova, and the thermal energy of the galaxy are all about the same. Which is kind of fascinating, but also the galaxy's like 10 billion years old. Everything's going to equilibrate. Everything, like if you've got one source of energy and you can couple to it, you're going to dump energy into it. So is that observable? You got to measure each component and compare them. So there's not one good measurement that says, these things balance. See. What is Rij? I'll talk about that in a second. What is Reynolds stress? I'll talk about that. Can we confirm the turbulence in small stars? We can, because the equations of stellar structure are really well understood, and the impact on how the star looks is really pretty well understood. So we can't go in and say, here is a turbulent star with a very few exceptions. But we can see the sun. We know the sun is turbulent. And there are a couple other stars that we've been able to image, and we know that they're turbulent. So we have direct proof. But also, the fact that we can write down the star mass and put them on the HR diagram, it works so nicely because we understand stellar structure pretty well. My friend Casey would argue with me and saying that we don't, because we don't really understand the turbulence, and everybody fakes the turbulence with mixing length theory, which is kind of bullshit. But we understand it pretty well. Mixing length theory works pretty well. How do we see turbulence? This is a really good question. One of the big things is looking for the power spectrum. So you look at the velocity fluctuations, and if you see that they follow this power law, what is a power law? What does this really mean? So I write down this thing, and it's a straight line in log space, or it's a power law like this. But what this means is that you have structure at all scales. You have structure at big scales, and you have structure at little scales. You have structure at all the scales in between. And so what does that look like? That looks like a fractal. That looks like a chaotic mess. There's not really, you can't look at it and say, oh, here is the large scale and here's the small scale. You have to measure that. But measuring the power spectrum is really the way we see turbulence. Mixing length, dynamo, galactic magnetic field, I talked on. Okay. What is Rij? Let's talk about that. So I'm done with questions. Does anybody have any questions on the questions? Now, oh, no, it's here. Now what am I doing? I'll show you the structure function thing later. Let's talk about turbulent diffusion. And so I'm going to talk about turbulent diffusion the way the book does it, and then the way Richards did it with potatoes in a lake in Scotland. And that will flesh out this whole story. And then if I still have a minute, which I should, I'll talk about the Reynolds stress. Because that's, and maybe I'm going to wind up talking about Reynolds stress on Thursday as well. Because it takes a second to get your head around, because there's just a lot of pieces in it. So we talked about this tensor Rij, and we defined this as Vi at x, and this is Rij is a function of R, and we define this as Vi at x times Vj at x plus R, and we average this over x. So I take every point, so for every point in the box, I'm going to average over all x. So for all points, I look at what, this is my vector R. I take this, and I move this to every point in the box, and I average what I get. Now, because turbulence is isotropic and homogeneous, I know, okay, this is complicated and horrible. So what does this tell me? So if I plot this is R, and this is big R of R. If I plot this, I'm going to get something that's kind of like, well, what should it look like? It should look like V squared at R equals 0, right? Because at R equals 0, this is just V squared. It's just V dot V averaged over the whole box. So the beginning of this is V squared. And then as I move further away, when I do this average, I'm going to get, sometimes it's going to be higher and sometimes it's going to be lower, and I'm going to have this fluctuation where I pick my velocity here and I take all the points. Let's just think about all the points that are radius around here. Some of them are going to be higher, some of them are going to be lower. Some of them will be higher, some of them are going to be lower. So if whatever is at this radius is not correlated with this, then when I add them all up, I'm going to get 0, because I'm going to have just as much going up as going down. Does that make sense? You look confused. So I take my velocity here, and if my velocity is in this direction, and I have a bulk flow that's always in this direction, then when I measure the difference between this velocity and this velocity, since I know what these all are, I'm going to get something that's pretty regular, and I'm going to just get the average along this circle, and that's going to be the same velocity if I have a big bulk flow. But if I have a crazy mess around here, then for every time my fluctuation is large, I'm going to have another fluctuation that's in the opposite direction. And so I'll have just as many ups as downs if it's really truly random. Then this will go down to 0. So this changes right next to my point, right next to this point that I've picked. I have a pretty good guess what the velocity is. It's going to be pretty close, because you have some kind of length scale over which things are coherent, right? So what this R, so I'm simplifying this a lot. So you can simplify this thing a lot by saying first, Rij of R vector has got to be Rij of just the magnitude of R. It can't depend on the direction because of anisotropic. And then you can also say some things about using isotropic and homogeneity. You can say some other things about Rij, and basically it just turns into some correlation function as a function of distance. And I can average out which component I'm talking about. So Ij depends on the components, right? And now again, because of symmetry, if I rotate my universe, I switch I and j around, I should get the same answer. So it can't depend explicitly on I and j either. So my correlation function is just basically a scalar function that depends only on R, and it starts off at v squared, and then it falls down, and eventually it becomes 0. Does that make sense? So if I'm looking at how correlated one point is, so I pick a point in space and I want to know how likely is that to predict this other point here, I can look at this correlation function. And if it's large, then I'm likely to predict the right velocity, and if it's small, I'm not. So we can turn this into a length, and this is called the correlation length. All I'm doing is adding up the integral over here and then dividing by the base of just making a rectangle, it's kind of the dumbest thing you can do. You just make a rectangle and look what the length of the rectangle. This is the length over which you can expect things to be correlated. And if you're much longer than that, then you're not very well correlated, and if you're much shorter than that, you're reasonably correlated. Does that all make sense? So that's the important takeaway, is that the full details of this being a tensor is way more power than we need because we're going to make all these simplifying assumptions. Yeah.
What would be a case where like the correlation length is like really small or when it's really big?
Yeah, if the Reynolds number is really high,
Okay.
then the correlation length gets small. And for low flow, like we were looking before, that laminar flow, that ultra laminar flow there, the correlation length is the size of the box. I mean, everything's correlated to everything else. I turn that crank, and the whole annulus moves around in lockstep, and the whole next annulus moves out a little bit slower, and the next annulus moves out a little bit slower. So the whole thing moves in lockstep because it's very low Reynolds number flow. So there, the correlation function is the whole domain. Can't be bigger than the domain. That doesn't make any sense. But if you have something that's very chaotic, then the likelihood that your neighbor is going to be similar to you is pretty low. So now I can do this. I did this in space, but I can do this in time too. I can talk about the correlation time scale. So I can say, oh, I want this still. So now I'm going to call this R of tau, and I'm going to write a similar. I'm going to write a similar function, which we'll call R of t, which is the integral of, which is the average of v at t plus tau. And this is got to be, this function is tau, and we average over time. Same idea. I just say, okay, I pick a point in time, and then some point in the future. How likely is the point that I'm at now to predict what that point in the future is? And the further away I get in time, the worse it gets. And we can similarly define a correlation timescale, t, by doing the same thing. We just measure this somehow, and your measurement is pretty bad. And then you approximate it with just a number. And because we're doing an integral over everything, and the stuff that we're skipping is probably pretty small, the correlation length is probably pretty robust, even if the shape isn't really very well constrained. So we can describe some correlation time. Does that make sense? So it's basically, how long do I have to wait before I don't know anything about the solution? Or similarly, the correlation length is how far do I have to go before I don't know anything about the solution, given what I know here. So I wish I could just switch these two boards because I don't want to leave all that stuff up. But tough crap, I'll go to erase it. So we'll come back to this.
Both the graphs look the same, right? Like the
Yeah,
shape looks
the basic idea is the same. So they both start off at r equals 0. You just have v squared. And then as you move further away, it falls off in some fashion. And it's got to be kind of flat, and it's got to fall off to 0 somewhere. And it's probably not going to have some weird feature in the middle. Why would it be suddenly correlated at some other random ass time? So we can reasonably draw this shape. And even though this actual slope isn't right, at least the smell is right. The flavor is right. The basic shape is right. So then when I average over this to get a length, then I'm not throwing out anything that I'm really not missing too much. So now,
Sorry.
yeah,
So big T is like the difference between T and tau.
that's right. Yeah, yeah, that's right. So this is where T and tau start to care about each other. So this is going to now be big T here. Where now I'm keeping the curve the same because everything that I know is still the same. But now it's a function of time. And then my correlation time is going to be, I just add up all the correlation and divide by v squared, and I'm done. So what we want to get at, so for the next couple of minutes, and it might take me the rest of the time. What I want to get at is, how does the average of x squared depend on things in the fluid? So what does this do as a function of time, or as a function of space? But we talked about this as a function of time, so let's do that again. So, I gotta go back to my cheat sheet, where I did everything in a way that makes sense. That makes sense. What goes on the board may not make sense. Okay, so the average of x squared as a function of time is equal to the integral of, okay, so let's do just one. Average of x is equal to the integral from, at a function of t, is equal to the integral from 0 to t of v of t, dt. Make those primes so that we're being honest about our integrals. This is not an approximation. This is just what the velocity is, right? If I take a derivative of this, I get the position. And this is typically 0, because in most turbulent flows, I have just as many lefts as I have rights. So I'm not likely to move around very much, even though you know that I'm going to. So now the mean squared displacement, which is the thing that we actually want to measure, this is 0, and that's dumb. Or I can move to I can do a Galilean boost and move to a frame where this is 0. I can do that. X squared, however, is the integral from 0 to t1. No, integral from 0 to t. This is a function of t. Integral from 0 to, this is dt prime. Integral from 0 to t prime. V of t prime. dt prime. And we're gonna, does that make sense?
You get extra dt prime.
Oh, how many d? Oh yeah, too many dt primes, thanks. Okay. So now I've just got two velocities. Or you can think about this as squaring this, which is squaring that, and you wind up with this same integral. So I haven't done anything fancy here. I'm just writing down what x squared is. So now I'm going to call this, you can see that this is basically related to v squared times the integral of dt prime dt r t minus t prime. So I'm just plugging in, I have some correlation function as a function of time. We're going to call it r. Now it can't depend on t and t prime in any way other than the difference between the times, because we don't have any initial conditions. We're talking about some kind of steady state that has always existed like this. So just like this r can only depend on the length, on some kind of length, and not the actual vector position, this one only depends on the time difference. And so I'm pulling a dodge. This r is 1 at t equals 0, and we're factoring out our v squared. Does that make sense? So I was saying that r is 0 is v squared here. We're going to factor that out and say that r is v squared times this function, and this starts at 1 here. It's just moving things around. So we're going to talk about a couple of regimes. So now I have some correlation time, big T, and that is the time at which, so my correlation function r of t minus t prime, is going to start off here at 1 and fall off to 0 somewhere. So now if I'm looking at times that are very close to each other, then Rij is essentially 1. And this is just 1, and I get a t from here, and I get a t from here, and I'm left with x squared of t equals v squared t squared, big T squared. That make sense? Because the only thing that's going to be left from this integral is big T squared. Oh, I'm sorry. Wait, back up and delete that sentence. we'll just call this t, we'll call that little t squared, because that's gonna change with time, because as you move outwards, but this is only true very short times. So here, I've got x squared goes like t squared. This is basically ballistic motion. Right? This is just things flying because of the velocity. If I know, if I have a uniform velocity, then x equals vt, right? So if I have a uniform velocity, x squared equals v squared t squared. So this is ballistic motion. So this is also just ballistic motion. This is just things have a velocity and they go. And that's it. That's all you know. Because the velocity doesn't have any other interesting information about it, because we're only talking about short little correlation times. So we basically know the velocity. So I can't tell if this JK is joke or somebody's initials.
Oh no, I was astronomy lab yesterday and we went to Silver Lake Park.
Oh yeah. Oh, who's JK?
No, that was just, he was saying joking. That's
Okay.
yeah, Christian was teaching this class.
Okay.
I wasn't the other one.
Oh, okay. So he wanted you to get there by using the stars.
Yeah.
I had the, okay. So I spent an afternoon learning how to navigate by stars because I was sitting in my office, typing away, and this guy shows up and he says, "I'm looking for an astrologer." And I'm like, I'm in my office, I can't get out of this.
Looking for the
I
sign
have to
of the
talk to this guy. And I'm like, but my MO is never assume anything. Like that's what my reaction said, but on the outside, never assume anything about what that person, like somebody shows up wanted to talk to astrology, I'll talk about them and then I'll tell them stuff. But let's just see where this dog goes. So I talked to him for a couple minutes and he's like, maybe I'm not looking for an astrologer. I'm trying to learn how to navigate. I have some star coordinates and I'm trying to find something. And I'm like, what? You don't want an astrologer. You want me, actually. It turns out he's looking for some buried treasure. He has some family documents that have the star positions where they buried something, and I could not get out of him what it was. I know. I know. So he's like, I have these star coordinates and I have this location and I think that it's around here. I just need to know how to turn star coordinates into physical locations on the ground. I'm like, oh, you don't want an astrologer, you want a physicist. So we wound up talking and then I never heard from the guy again. But I saw him twice. He came by my office on 2 separate occasions. And then I was like, okay, this guy's, once I saw him the second time, I'm like, okay, this guy's for real. I'll actually answer his questions. So I spent half a day and read about how to navigate by the stars. It's hard. So anyway, listen, when you don't judge people until you've really heard them out. You never know how interesting it's going to get. So anyway,
Isn't it just a system where you translate the sky sphere onto Earth coordinates?
Yeah, more or less. More or less you have, I'm standing here, I have a star up here, I know where that star is directly overhead, and I know where that star is for me, and I know this angle theta translates to this angle theta. More or less. We'll call that theta prime because it's not direct. But yeah, it was interesting. It's beautiful.
The easiest is Polaris because the altitude of Polaris gives you your latitude.
Right. Yeah, but that's a really good one. So anyway, okay, where was I? Correlation functions. Okay, so first, if L is really, really small, if L is much less than the dissipation length, then average x squared goes like the diffusion constant times t. This is what we did yesterday. What we just did, you can make a basically identical argument. Like there's no, we waved our hands on this argument, right? I didn't skip anything. I showed you the whole derivation. There's a lot of hand waving. You can wave your hands with length. the same. So if L is of the order of the dissipation length, maybe a little bigger, then x squared is going to go like v squared t squared. And you get this ballistic motion. So now with this same argument, what do we get if yeah, so with the same argument, so this is just a t. With this same argument, if I say that now my extents go way, way, way past the correlation time, so if t is way bigger, so the correlation time is t here, if the correlation time is way bigger than t, then this first integral just gives you t, right? And then the second integral gives you another t. So then when t is much larger than the correlation time, then x squared goes like d times the correlation time, big T. This is slightly different behavior. So now 3, you can make an identical argument with length scales. So if L is much, much larger than the integral scale, I'll talk about the integral scale again in a second, then x squared is proportional to some diffusion constant times the integral time. Oh, I got 10 minutes left to do the intermediate spot. Okay, so what the book covers for turbulent diffusion is either if you're much smaller than the integral scale or much bigger than the integral scale. What's the integral scale? One of those things that I forget to talk about. E of k has this behavior where you have injection, inertial range, and dissipation. So this is injection. We'll also call this the integral scale. So this is where if you add everything up, that's what the energy is. If I add everything up, I'm not going to find this energy, I'm going to find this energy. And then this part is called the inertial range. And this is dissipation. So if I'm way down here, below the dissipation scale, then I have molecular diffusion. If I'm at the bottom of the ballistic scale, the integral scale, or the inertial range, then I get ballistic motion again, because things just kind of move together. I'll talk about this in a second. If you're way over here, way bigger than the turbulence scale, then it goes like diffusive motion again with a different d, a d that comes from the velocity. Oh, let's actually write down what this d is. Oh no, d of t is just the integral over this. There's nothing more you can get from that. So let's talk about what happens when you're in the middle of the inertial range. And this the book doesn't talk about. I'm kind of mid on the book's description of turbulence. I would do it differently, but I also have the advantage of we have a lot more turbulence study. So let's talk about Richards diffusion. So Richards was a fluid dynamicist, and he threw parsnips into a lake and measured how they went out and found this relationship. And this one, you're going to hate this derivation. So we showed, when we were showing the Kolmogorov cascade, the velocity goes like length to the 1/3. Everybody, that should be familiar. If anybody doesn't remember why this is, I will do it again. Everybody cool? At least cool enough. You'll have to do it in a hallmark. So velocity in a turbulent fluid goes like the energy injection rate or the dissipation rate. They're the same by assumption, times L to the 1/3. So this is equal to dl dt, right? So L times dl dt is dl squared dt. As a 1/2 in front, if you want to be, which is epsilon L to the 4/3. So if I just integrate once, how does this work? I got my dt goes over here, my L comes over here. You're left with L squared, and treat L squared as the variable, because that's the variable we're looking at. So you integrate this L squared variable, and you find that L squared, to the L squared, let's just do it, the minus 2/3 equals dl squared equals epsilon dt. So L squared to the 1/3 equals t, or L squared equals t cubed. So if you're in the middle of the inertial range, x squared is going to go like some diffusion term times t cubed. And you have superballistic diffusion. So why is that? Because the velocity gets bigger as you get further apart. So if I'm just feeling the random banging around of molecules, then I'm going to randomly walk around, and so will my buddy, and we'll just randomly walk around, and we'll separate like t to the 1/2. But once I get onto the turbulent cascade and I'm on that inertial range, then the velocity gets bigger as you get further apart. So you've got some velocity separation between 2 points at some velocity. As they get a little bit further apart, their velocity separation gets bigger. And as they get further apart, the rate that they're separating gets bigger. And as they move further apart, the rate that they're separating continues to get bigger, faster. So you get, in the inertial range, the mean squared displacement goes like t cubed. So we have these 4 different ranges that we need to think about when we're talking about turbulent diffusion. Okay, is that still right? Yeah.
It's actually right now. Yeah.
I fixed it right when I started.
Oh, okay.
The test does it get bad during class? Okay. I'm gonna start Reynolds stress, but I'm not gonna get very far, and then I'm gonna start again on Thursday. But Reynolds stress takes a second to get your head around. So these diffusion things, you gotta remember which approximation to use when, and how to wave your hands around those things. But this board here is something to definitely keep your head around, okay? Because questions will show up from that. Okay.
So, sorry,
Yes.
you said that the D at the top and the D at the bottom are different?
Yeah, so this is the molecular diffusion constant. This is the turbulent diffusion constant, which you don't really know, and this is the big turbulent diffusion constant. So they all get different diffusion constants because the underlying physics is different. So the first one is molecules bang into each other. And this one is an integral, this D is an integral over the correlation function.
And those are all dispersion relations.
I'll call them diffusion relations. Because notice that for each one, we're measuring the mean x squared, mean x squared, mean x squared, mean x squared. So we're looking at the RMS the RMS distance between particles as they're mixed in here. So what you can see is the turbulent mixing, proper turbulent mixing, is much faster than waiting for your coffee to just diffuse. If you put a drop of milk in a coffee cup, it'll take several hours or days for that milk to properly mix, or you can do it in half a second with your hand, and your hand has turbulent motions. Okay, so remember how when we linearized stuff, we said rho equals rho naught plus rho 1. We plugged it into the equation. We get rid of the nonlinear terms, and then we subtract off the background solution that we already know. And then we have something that we can actually integrate, and we get something that we can solve. It's really this throwing out of the rho 1 squared, but also taking off the background solution. So now what happens when we can't do that? So now I'm going to show you what happens to Navier-Stokes if we don't throw out the square terms, because now we can. So we're going to call our velocity, we're just going to think about velocity for a second. Velocity is going to be some mean flow, and this in principle I have some kind of handle on, like I've got a hose and I know how fast the velocity is coming out of it, but I want to know what the turbulence is doing inside the hose. So I have some mean flow plus some fluctuating flow. So if I average V, I get the average of V bar plus the average of the fluctuating term. You know that I need to just get V bar again. So V bar bar is just V bar. The average of the average is just the average. Because once I've taken the average already, it's constant with respect to whatever I want to take the average of. Right? So if I have some quantity Q of X, and I average that over X, this is now a number. If I average it again, I just get that number again, right? The average of the fluctuating terms is all 0. Now, what do I mean by average here? So in the most general case, we mean the ensemble average. So we run the experiment 500 times, take the output of all 500 experiments, average that. That's really hard to do. So what you instead use is ergodicity. And you assume that after a certain correlation time, if I move a correlation, several correlation times away, those are different experiments. Yeah?
So, I forgot my question.
Ah, I'm sorry.
It's okay, it's okay.
If it comes back to you.
Just come back to me.
Yeah.
Um,
And that's actually all I'm going to say. So what I'm going to do is take this.
Oh, sorry.
Yeah.
Okay, so is the reason that the average of the prime, does that come from the anisotropic assumption, or is it just-
No, I'm just assuming that it works this way.
Okay.
So I mean, I'm just saying that I've got some mean flow and some deviation from that mean flow. And because when I measure it, I should get the mean flow again, the fluctuations have to average out to 0.
Okay.
So it's kind of by construction,
Okay.
if that makes sense. So what I'm going to do is I'm going to take this, drop it into Navier-Stokes, average it, and we get something that looks just like Navier-Stokes, but we also have this extra term that looks like V prime bar. Because I can average two fluctuating quantities together, that's not going to be 0. But I get a term that looks like this, and this is the Reynolds stress. So then you have to talk about what this actually means, because now I have an equation that doesn't look like the Navier-Stokes equation anymore. But that's still supposed to be describing the flow. So we'll talk about what the actual implication is. We'll do the math so that you see it, but the result is easier than the math. Interpreting the result is not easier than the math. Okay, that's all I got for today. We'll do some more next week. Oh no, Thursday. Okay, so my promises to you are there will be a homework up tonight. There will be office hours next Monday. I will have everything graded by the end of the week. And then we'll have a midterm on next Thursday. And we'll review, so bring up your questions for next Tuesday.